let's plan on finishing up the 6-2 notes here. We'll take some questions from you guys after that, and then we're going to take some time today to just do some more of these volumes of revolution practice together, because it's not easy, right? You've probably tried a little bit of the homework by now. It can be pretty tricky to get things set up correctly. And I be clear, like, that's super normal. Like, that's super duper normal. Okay? But we'll get better at it. But let's finish up these last two examples together and then get on with ourselves. Okay? So here it says that we have a solid with a circular base of radius 1, and then parallel cross sections perpendicular to the base are equilateral triangles. And we're asked to find the volume of the solid. So our area function is going to be triangular, right? So if we think about, notice that we're not given a equation anywhere in here, so we're going to have to kind of make our own. That's okay. So if I just kind of embed the xy axis here, and I draw in our that circular base or whatever, so that's like the base of this figure, right? Everybody's cool with what I've just drawn there? It says its radius is 1, so I know this point is like -1, 0. This point is +1, 0. This point is 0, -1. And this point up here is 0, +1. Everybody's okay with that so far? Okay. So what I'm going to be doing is I'm going to be taking, or what we're going to be doing is we're going to be taking like triangular cross sections. So like that's going to be like the base of my equilateral triangle, right? Again, it says that the base or the area is an equilateral triangle. Is okay with that? So this is like in green, that's like one side of my equilateral triangle. So far, so good? Okay. Let's figure out the length of that side S. So what's the equation for our circle? X squared plus y squared is equal to 1. Great. And the distance for S is like a vertical displacement, right? So it's basically like, you know, we have x comma y and x comma -y, so this is going to be like 2 y's. Everybody buy that? Well, I mean, like, how far is it from the x-axis up to here? It's y. How far is it from the x-axis down to there? It's y. So 2y for s. So what I'm going to do then is I'm going to solve my x squared plus y squared equals 1 equal to y. So I have a side length for that. So we can subtract the x squared from both sides, square root both sides. And we have plus or minus square root of 1 minus x squared. Since y is a distance in our picture, or since s is a distance, I can drop the plus or minus and just call it positive. Everybody's okay with that? Now, how are we going to find the area function for this equilateral triangle? How do we find the area for a triangle? 1/2 base times height. Do you know any other formulas for the area of a triangle? It's 1/2 AB sine C, right? Was the other one we know. Does anybody remember the formula for an equilateral triangle? There's a specific area formula for an equilateral triangle. That was something you probably saw in geometry, but that was a million years ago, and I don't even really remember what the formula was, but there it is. It's square root 3/4 side length squared, which would be particularly handy if you remembered that. Everybody agree? What would be the least handy of them? The 1/2 base times height. Why is that the worst one? We don't have the height, right? It would require doing a lot of extra geometry to get it. Hopefully, we would remember 1/2 AB sine C, because we have everything we need for that just from our triangle. And since it's equilateral, it doesn't really matter, like every angle is 60 degrees, every side is the same, so it's whatever. Anybody remember what sine of 60 degrees is? Yeah, root 3/2. Shocking that if we simplify that now, we're going to have root 3/4 side squared, which was our area formula for an equilateral triangle that we just looked at. So not a disaster if we didn't remember that. And that just simplifies now to so let's calculate our volume then. So that's the integral from -1 to 1 area of our cross section dx. Anybody notice anything handy we can do with this? What's that, Mackenzie? It is an even function. Good. So we can do the even formula to make that a little bit easier for us. Absolutely. Good eye. Oops. And that happened a bunch on the homework, so I'm not surprised you saw it right away if you've tried the homework. You had lots of opportunities to apply that. Is it a disaster if you don't? No, but it saves us a little bit of like annoying computation, right? Because plugging 0 into this is going to be massively nicer. And I'm going to pull the square root 3 out as well. And now we're ready to do some antiderivatives. So the antiderivative of 1 is just x. The antiderivative of x squared is x cubed over 3. We're going to evaluate that from 1 to 0. And the nice part about that is that when we evaluate at 0, it's just 2 zeros. So what did it do? So we end up with 2 root 3 times 2/3, or 4 root 3 over 3. How'd that feel? What was the hardest part? Getting that set up, right? Getting that area formula for our cross section was the tricky part. Once we had that, though, the calculus piece was pretty easy, right? All right. I think I have one more example. Is that questions on this one before we move? It says find the volume of a pyramid whose base is a square with side L and height H. Notice I didn't include a picture for you. So how are we going to do this using calculus? Obviously, you could do this if you remembered your volume formulas from geometry. You could do this geometrically. Well, the first thing I would do is I would go and embed this on an XY axis. And then I'm going to have try to do my best drawing this in 3 dimensions. I'm no artiste. And we'll say that this is the point where the face of that, or the base of that pyramid is exiting, or the x-axis intersecting the base of that pyramid. Everybody okay with that? So that point there is h comma 0. Since the height of the pyramid needs to be h. And that okay there? So my area function is going to be the square, right?
Back to the h here.
Mm-hmm.
So h is the height of our square.
Height of the pyramid.
Pyramid. Oh, okay.
height of the pyramid. Squares don't have heights.
Right.
Yeah. Yeah. Is that cool there? It says the square has side length L. So obviously at the base, the cross section is L squared. But what's that gonna be like at some arbitrary spot here? Say this is like x comma 0. What is the size of that square going to be? Thank you. Paul, it's for you. I don't know. Between classes. Does this picture look familiar to you? I know it's a geometry picture that we're calling on. It should look like the dilation picture. If you remember when you did dilations in geometry, where you took like an image and you enlarged it. The picture we drew was exactly something like this, where like this would be like your pre-image, and that would have been like your image. Does that ring a bell now when we kind of use that vocabulary? Seeing some head nods. Do you remember the important thing about a dilation? They're proportional. Yeah, exactly. Exactly. So what we want is we're going to say that I'm going to call this side length here S. We know this side length over here is L. So I know to find the length for S, we have like S over X is equal to L over H. Or that S is L over H times X. So that's the side length of the square at any arbitrary value of x between 0 and h. So the area for that then is going to be that proportion squared. Everybody feel okay with what I did there? All right, so let's set up our integral. What are our bounds on our integral? We're going to integrate from 0 to h. Excellent. If you know it, shout it out loud and proud so we can give you credit. I just hear whispers. And the area function we said was L squared over h squared times x squared. And we have the dx. Okay. How do I integrate that? Good. I can pull out the L squared and h squared because those are constants. The variable I'm integrating with respect to is x. So really, I'm just integrating x squared, and that's an easy integral to do. Oh, that was supposed to be an h up there. It just, my bad penmanship made it starting to look like an L, and I was like, why does that look like an L? It's like, that's not right. So we do that, and we simplify down, and what do we end up with? L squared h over 3, which again should be no surprise, because what is this? This is 1/3 area of the base times the height, which I know is the volume formula for a pyramid. We've just kind of derived it using calculus. Everybody cool with that? That's our final answer. All right. I know it's a lot. Hopefully you guys have tried a little bit of this Chapter 6 homework. Let's start with some questions from Chapter 6 things. So 6-1 or 6-2, either is fair game. We'll hit some questions, and then the rest of the class will kind of do some guided practice in the 6-2 arena. Nia? Absolutely. Yeah, for sure. And again, I want to be clear. It is okay if this feels really hard. It is okay. You are not like in over your head. You're not like dumb. It's not that you're not going to get it. It's just hard because you need to like really be able to get a good picture out of it to figure out what to do. And that's not easy, right? It's not easy. All right. Now I want to ask you what we want to do with this. Do you want me to start from like the hardest possible situation? We're going to generate all of our pictures from hand? Or do you want to start with, I'm going to use some technology to get a decent picture out of this and then look at what I have and build my integral from there? You tell me which one you want to try. Mian, I'm going to direct that to you specifically. Either is appropriate, right? Like more likely than not, this would be a calculator question on an AP exam. So I think that having your calculator to generate a graph is not unreasonable. Now, for me to be able to drop this in, I'm going to use this Graphmatica program because it just makes it a little bit easier for me to drop the image in. And the images I'm going to get are a little bit nicer than the, I just have better resolution or whatever than your calculator is going to give us. So I have y equals 2 minus 0.5x, and then y equals 0. Oops. Y equals 0. X equals 1. And x equals 2. So let's put that back to its regular size. Copy that in. Oh my, that is a big daddy picture there. So like that's the piece that we have, right? And it says we're going to rotate that about the x-axis. So what are we looking at here? Yeah, it's going to look like a cone without the tip, right? So from like our three-dimensional figure, it's going to look like that kind of thing. Now that's hard to see right away, right? That takes a little bit of practice, getting used to like closing your eyes, visualizing that in 3 dimensions. But it should be something that's reasonable to do. Everybody's okay with that? Okay. So if I'm taking my cross-sectional area, that's going to be a circle each time, right?
I'm confused. I thought the circle was on the circle or something like the other part. Like I'm confused.
Oh, should I have drawn it this way?
Oh, well.
That's the way it, like what you're going to end up with when you do the rotation around, because we're rotating about the x-axis.
Yeah, I guess I'm confused how you got that shit from our 2D.
Sure. So this is what's happening, right? Like this is spinning around in 3 dimensions. So like this line becomes like the radius of a circle that spins around.
Oh, okay.
And then this line becomes like the top of the radius of the circle that spins around. Does that?
I got you.
Yeah. Okay. And again, like once you see it, it's like, okay, I got it. But like it's hard to talk that through, right? Like you just got to kind of.
Just a reflection and not like.
Oh yeah. It's a full rotation, so you're getting a 3-dimensional figure out of it. Okay. So like that's like a cross section, right? As a circle. So the area for a circle is pi r squared, correct? So this would be like the radius for my circle. So that point would be like x comma y, where the radius would be the y coordinate at that point. Does everybody feel okay with that explanation? How do I find the y coordinate at that point? That's a point on the line, so I can use that equation, 2 minus 1/2 x. Now, probably should have said something from the jump that we probably should have said before we dove in doing this. I'm doing this integrating with respect to x. I hope that would be super obvious because it's all along the x-axis, right? That the central hub of this 3-dimensional figure is the x-axis. So like it starts at the base starts on the x-axis and it ends at the x-axis. It feels like that should be pretty obvious that I want to integrate with respect to x. But we should have said that expressly at the beginning, because that wouldn't always be the case, right? For something like this, definitely would be, but like not all these ones you'll want to integrate with respect to x. Okay. So let's set up our integral now that we've identified our area function. What are the bounds for our integral? 1 to 2, yep, because we're just going along the x-axis. We have our area function with the dx on it. Everybody okay with the setup so far? To do this integral, how do we want to do this? You could U sub it. I would not. I would just FOIL that out. I feel like that's going to be easier, but U sub will work. It's not wrong to do it that way. Oops, that's a 2x there, sorry. And then I'll just do my antiderivative from there. And at that point, can I leave this stuff for you guys? Yeah. Did that help? Again, the hardest part is kind of visualizing what's going on, to see what those cross sections are, to envision where the radius is, draw a lot of pictures, draw a lot of sketches for yourself. It really, really helps, especially in the beginning. The hardest part is seeing what the three-dimensional shape is supposed to look like, and then being able to draw your cross section and figure out the area of that cross section with respect to X or Y, right? That's the hardest part. After you've got the setup done, the calculus piece is pretty easy, right? Doing the integration, I think, is probably not a problem for us, right? The problem is the setup. All right, let's try another one. Yes? And we'll go and work on these ones that you guys have worked on here for a little bit, and then we'll try some of them that we haven't done yet. But I think in the beginning here, it's probably most helpful to start with the ones you've already thought about a little bit. If you've started the homework, which I assume that, 50% or so of us have, which is pretty normal. Okay, so let's look at 3 next. Again, I'm going to start by generating a picture. Let's again just use technology to kind of generate that picture to start. When we get a little bit more practice, we'll talk about generating that picture by hand. Do you want to skip to 5? You'd have to get the y by itself. So you'd have to do some rearranging to type that into your calculator. And you might need 2 lines to get it in if you have like a plus or minus thing going on. But we can skip to 5 if you want to skip to 5. I probably would still do 3. Let's do 3 again. That's a little bit more obvious what to do, just as we're getting used to things. So this is my picture. Everybody should feel good about, if we're rotating about the x-axis, we're going to be integrating with respect to x. And we're going to integrate from 1 to 5, right? Everybody feel pretty good about identifying that just from looking at our picture? So,
wait, did you go to the problem? What are the... Oh.
Sure thing. All right, so let's go and resize this so it's not gigantic. So again, the area that we're looking at is this thing. We're going to be rotating it about the x-axis. What is my three-dimensional shape going to look like? It's not a cylinder. It's kind of like your fingertip, right? It's going to kind of look like a finger. So like we have a circle at one end, and then it'll go down to like a tip, like a thimble shape or something. Does that feel okay? Or maybe like a test tube? That's maybe a better word for that. You guys buy that? Okay. So again, like my cross section is just going to be some circle like this, right? The radius for that cross section then is going to be just the y, right? Does that feel okay? And the y coordinate here was the square root of x minus 1. So my area function would be pi times square root x minus 1 squared, or just pi times x minus 1. And so I think we're probably good to set up our integral now. The bounds of our integral, we said we're going to be from 1 to 5. And then we have pi, I'm going to stick that on the outside, x minus 1 dx. And then from there, I'm going to let you guys handle the annoying parts. Not that the first parts weren't annoying, but like the tedious parts. Where just like, I got to plug some numbers in and deal with a bunch of yucky fractions or whatever. Not that it doesn't take, 30 seconds on your calculator, but that's 30 seconds I don't want to invest. Mostly because I want to use our time to talk about the stuff we're not good at. Typing stuff into the calculator, I think we're probably okay with it. That one feel easier? Doing a second time? They should, right? They should start feeling a little bit easier as the more that you do and the better you get at like visualizing what's going on. The nice part is the procedure is basically the same. All right, let's look at 5 then. Notice that 5 is different in that we have an equation defined in terms of x and is being rotated about the y-axis. So if you wanted to try to type this equation into your calculator, you'd have to get the y by itself. So you'd divide by 2 and then square both sides. So you end up with x squared over 4. The nice part about the program that I'm using here is that I can type in my equation in any form and it will handle it just fine. So I can just type in x equals 2 times square root y and it just puts it in there for me. So there's my picture. Oops. I guess we'll take it from there. Okay. So my area that I'm going to be rotating is this one right here. That's bounded between the curve below y equals 9 and to the right of x equals 0. But this time we're rotating about the y-axis. What's this shape going to look like in 3 dimensions? Yeah, another test tube, right? Same shape as the other one, it's just this one is vertical rather than horizontal. Woo! Dee-doo! So I'll kind of start the same way. I'll take my cross section. So there's my radius for my cross section. The radius for my cross section is going to be represented by which coordinate this time, though? X. Yeah. And I know that the x coordinate here is 2 root y, comma y. Or the coordinate there would be 2 root y, comma y. So my area, still a circle, so pi, and then my radius here is going to be 2 root y squared. Oh, probably should mention here, what have I assumed automatically that I didn't mention that we probably should mention? We're going to integrate with respect to y. Yeah. Hopefully that's super obvious, right? In general, if you rotate like the horizontal on a horizontal axis, you're going to be integrating with respect to x. If you rotate about a vertical axis, integrate with respect to y. That's not hard and fast, but it's probably pretty good for where we're at. It doesn't have to be that way, but like, you know, it's most often that way. So my area is 4 pi times y. So we're integrating from 0 to 9 of 4 pi y dy. So that's just going to be 4 pi times y squared over 2 and evaluated at 9 and 0. Is this feeling better? It's starting to feel like they're kind of all the same, right? It's like, okay, I can handle doing this. So the discs, this is what we're doing right now. These are all discs, right? Because the shape of the cross section has been in a circle, are typically much easier than the washers. We'll do a washer here in a second. But before we do that, let's give you guys a chance to do one of these on your own. Why don't you guys try number 6 on your own? No, let's not do that. That makes no sense, Mr. Kulik. Why not, let's do 7 on our own. Why do one that we haven't, like, that we don't have to do for homework yet, right? Do 7 on your own. Let's make it productive, right? You guys are all getting ready to yell at me. So take out something to write with or use your OneNote or whatever you're comfortable with. We'll take 5 or 10 minutes here, work through number 7. I'll scroll back so you guys can see the problems. And again, like, if you don't have your calculator with you, like, don't worry about it. Like, just go to you do the plugins, right? Like what we've done here before, where I just quit after a while, where I'm just like, okay, it's just calculator time from here, and I don't want to do it.
What's the last x? Does it say
Greater than or equal to. Oh, shoot. Oh, well. What did Mr. Kulik do? This is a washer problem, isn't it? That's pretty dumb. No wonder, right? Okay, we'll come back and do that together. You guys do 6. What I originally wanted to do, and then you convinced me otherwise because it wasn't a homework problem. Why? Oops. Well, you just are talking about the area here.
That.
Yeah.
Oh.
And you're
Oh,
rotating
never mind.
about the
Oh,
Y.
Okay.
So it's another one of those, like, kind of like a cone with the tip cut off,
Even though it's like
but it's like a
concave.
convex,
Sure.
or yeah, concave cone or whatever. So maybe it looks a little bit, you remember like that game Sorry? How the pieces are kind of like that?
Yes.
It's like one of those with the tip cut off. Best I can come up with off the top of my head of something like you might be familiar with looking at. I don't see a lot of concave three-dimensional figures in everyday life. Is everybody integrating with respect to y on this?
So like number 5.
Mhm.
Like that. So when we find like an arbitrary circle,
Mhm.
our radius would be x, but we want it in terms of y. So we have to move the original equation around.
Mm-hmm. Absolutely. try to do this one.
The Y. Like I forgot how to plug it.
That's right. That's very good.
Like there's no unit, it's just like unit square.
Cubed, it's volume.
Oh, wow. Do we have to write that? Or you just
Usually we just write the number. For a problem like this where there's no context to it.
yeah.
Yeah, that's the same thing as e to the 2y. Yep. So to integrate that, you would use yeah. And might as well do that. I think that's our final answer there, I suspect. I guess I should look it up. Yep. What'd you guys think? Frustrating how quickly I do it, but should have felt easier, right? Better idea of what to do. Better idea of like, okay, I need the x coordinate. I guess I just have to rearrange this equation. No big deal. It's dead on. So I think that's, you guys feeling a bit better on some of these? Should we do some washer ones? Those are usually a little harder to see what's going on. All right. Okay, so this was the graph for 7. That's kind of big. So what's the three-dimensional shape going to kind of look like? Well, it's going to have like a ring, and then it's going to kind of like that. So it's going to be like, it's like an open, and then it's like one of those inverted, it's like the negative of the sari piece, like would fit inside of it. It's like the negative space of that. It's like a cone with then the sari piece like carved out of it, kind of. You guys kind of see that? Or like a chocolate kiss carved out of it or something? That's kind of what that should look like. Now, I did a poor job of drawing my picture, but I can see it in three-dimensional space. But boy, gosh darn, that's a hard picture to draw three-dimensionally. Okay, so the key is, though, that when I look at this, the cross-section is going to be a washer, right? There's going to be a disc with a hole in the middle of it is my cross-section. So I have like my outer, it's just not, I need a thinner pen. How do I do that? There we go. Give me that little skinny guy. Draw this fatter or something. Ugh. Going to look something like that, right? Let me just kind of draw it off to the side where it's like not embarrassingly small. So there's like my x-axis, right? You like how I did that in perspective too? Yeah. Busting out my art skills here. Okay. So just some arbitrary value x. This would be like my inner radius. And then like this would be like my outer radius. Everybody's okay with that? So the outer radius is going to be the y coordinate, right? From some xy. Which function is the outer function? Is it the linear one or the x or the logarithmic one? Outer is the linear one, yes. Good. Let me get a different color here. So you can draw that in if that helps you kind of see it. And what was that linear function? It was just y equals x. Obviously, I guess we should have said, or what are we going to integrate here with respect to x or y? I would do x, yeah. So this is just x comma x then. So my outer area is pi x squared. Everybody's okay with that? And then my inner radius is going to be like the y coordinate for that function. And that is the equation y equals x cubed. So my area for my inner function should have a of x is going to be pi and then x cubed squared. Everybody so far so good? So we'll start setting up our integral. We're going from 0, and it's going to be the area of my outer minus the area of my inner dx. What is going to be the upper bound for my integral, my b value? Is that, right? Where those two things intersect? Well, at 0 and 1. Everybody's cool with how I got that? Okay. And so now we just plug in. So we have pi, well, let's factor the pi out, right? So I just have x squared minus x to the 6th dx. Mr. Kulik, shouldn't that be negative? Right, isn't x to the 6th bigger than x squared? How am I getting a negative volume out of there? Look at the values for x we're plugging in. They're numbers 0 to 1. If I take a number less than 1 and I square it, it's going to be a bigger number than if I take a number 0 to 1 and I put it to the 6th, right? 1/2 squared is 1/4. 1/2 to the 6th is 1 over 32, or 64, right? So we're good. So we have x cubed over 3 minus x to the 7th over 7. Evaluated from 0 to 1, and this one is not so annoying. 1/3 minus 1/7 is going to be 4/24, or 21st, excuse me, 4 pi over 21. 7 over 21 minus 3 over 21 is 4 over 21. Again, you have calculators for that. Like, don't feel like you need to mental math that, but I decided to go all the way to the finish line because I could mental math this one a lot easier than the other ones, which are just were kind of uglier because they didn't have the 0 in there for us. Do you feel a bit better on this? So we still have we didn't do another example of the trickiest type where you have a washer and you're rotating about not one of the x and y axes. Let's at least talk about the setup for one of those real quick. So maybe let's look at 13. Does that sound okay for you guys? These are kind of the worst ones, although sometimes they're not really that bad, but they can be a little tricky. Y equals 1 plus secant x. Y equals 3. And then we're going about y equals 1. And I'm going to just make that dashed or something. Oops, that wasn't the one I wanted to minimize. Okay. So that's the piece that I care about. And I'm going to rotate it about this line y equals 1. So what am I going to get then? Oh, I goofed that up, but well. What is that shape going to look like? Huh? Well, it's going to kind of look like, I think it's going to kind of look like this, where the middle is empty. It's going to be like a reverse hourglass, where there's going to be like an hourglass shape missing from the middle, right? You buy that? Are we just like out of time here? Okay. We'll do some more questions on this stuff next time. Do the best you can with this. Hopefully you feel much better today than when we started.